Hello everyone, my name is Aishwarya. I am currently a performance and capacity engineer at Facebook. Today I am going to present our work, Pocolo, Power Optimized Colocation in Power Constrained Environments. This work was done during my grad school at the Pennsylvania State University, along with my collaborator Aditya Kumar and my advisor Anand Sivasubramanian. For the purpose of this talk, I consider a data center infrastructure as shown here. The data center draws its power from the utility power grid. The servers are the end units that consume power. Power is distributed to the servers using a power distribution hierarchy. A data center also uses energy storage devices and diesel generators in order to maintain availability upon utility power outages. The data center operators incur billions of dollars in provisioning and operating this physical infrastructure. The pie chart here shows the amortized monthly total cost of ownership of a data center infrastructure based on publicly available cost models. It shows that power infrastructure related capex accounts for a major part at about 27% of the amortized monthly cost. This is because it takes $10 to $20 to provision for each watt in the physical infrastructure. Similarly, power-related OpEx constitute another major component. Unlike the electricity bill that we get for our home energy use, data center electricity bill typically has two components. For example, the graph on the left shows the power draw of a data center in y-axis and the time in x-axis. The electricity bill comprises of the energy use of the data center, which is the area under the power usage curve, as well as the peak power draw component in the curve. Realizing the importance of reducing power related expenses, prior works have extensively focused on optimizing power infrastructure. These include works that focus on how to right size or oversubscribe the power infrastructure and the mechanisms to handle power contention that arise because of these optimizations. Traditionally, these works focus on a single tenant setting, where an application runs in isolation on each server. These applications might have different power draw profile. While these applications do not compete for server resources within a server, but they compete for provision power capacity, leading to power contention in the upper levels of data center hierarchy. Prior works have looked at how to mitigate power contention at this level. However, if we look at the total cost of ownership, servers account for a major portion of it. And to extract maximum benefits from provision server infrastructure, data centers typically stack multiple applications on the same server. So in today's system, we expect the servers to offer multiple cores, cacheways, high memory bandwidth, and there are policies and mechanisms to isolate the use of server resources. But power is also a shared resource, and applications compete for shared power capacity in a server. Therefore, in order to effectively utilize the entire physical infrastructure, one needs to ask the question of how to jointly utilize both server as well as power resources. To illustrate the problem of power contention, let's look at a scenario that's common in a private cloud. A private cloud infrastructure can profile the application and right size its server capacity and power capacity based on the peak power needs of the application for which a cluster is designed. However, applications do not always operate at their peak load. They are prone to diurnal demand variations as they are typically user facing and latency critical. This leads to spare capacity in server and power resources as illustrated here. To improve server utilization, the data center can place an opportunistic best effort workload on the server that runs the primary latency critical application. Here, we can use prior works to identify what applications to place such that we do not impact the performance of the primary latency critical application, but also utilize the spare resources in the server. However, if we do not consider power needs of the best effort application, we can easily overshoot the provision power capacity, which can lead to frequent power capping. What we observe using experiments is that incorporating power constraints can lead to different choices for colocation. For example, we have a web search server which is operating at a low load of 10%. In order to meet this load, the application only needs a fraction of the server resources. The server has 12 cores, but it only needs a single core. The last level cache has 20 ways, but the application only needs 2 ways. And the server power budget is 132 watts, but it only needs 73 watts. Say we have the option of co-locating any of the following best effort applications such as LSTM training, RNN training, compression, and graph analysis. The graph here shows the application in x-axis and its throughput normalized to running in isolation in y-axis. If we only consider spare server resources, we can place any of these applications as their performance benefits are identical. But if we include power as a constraint, where we cannot fully exercise the spare server resources even though they are available, we can see that only LSTM and RNN are better candidates. Similarly, one of the characteristics of the latency critical application is that its load is going to change dynamically, typically in a diurnal fashion. The graph here shows the dynamic range of the server from 10% to 90% of the peak load that the web search server can receive, and the y-axis shows the normalized throughput of the LSTM and RNN training in the presence of power constraints. This graph shows that if we only consider a server that is 10% loaded, as in the previous example, both LSTM and RNN are equally good candidates for best effort application. But we consider the entire range of operation. RNN is able to utilize the server resources better than LSTM. So the question is how to effectively co-locate application to improve overall cluster throughput. In order to identify effective co-locations, we need to jointly understand resource and power needs of the application. Towards that, we need to understand three aspects. As illustrated before, power is a limiting resource. Unlike other resources, power is an indirect resource in a server. It is consumed in all the direct resources like cores and cacheways. Therefore, we need to co-optimize power and other direct resources as opposed to independently managing them. Second, as shown previously, myopic placement decisions based on instantaneous load conditions can lead to inefficient placement or frequent migrations. So, we need to design to be aware of load fluctuations. Third, in contrast to achieving fairness, as in a public cloud, we consider a private cloud infrastructure in this work. Here, the goal is to maximize the server throughput while working within the constraints of the latency critical applications and infrastructure capacity limits. So, the key question is, can we systematically we can borrow principles from the field of economics to systematically and jointly address all the three aspects. For example, cost is an indirect resource which we need to buy goods like fruits and vegetables. There are methods and metrics in economics to maximize user satisfaction within a given cost budget while buying two or more goods. A problem is similar to that, where power is comparable to cost, an indirect resource, and goods are comparable to direct resources. Here, our goal is to maximize server throughput, which is similar to the goal of maximizing user satisfaction in buying goods as allowed by the cost budget. Specifically, we can use indifference curves to understand resource needs of the latency critical applications. For example, the x-axis shows the number of cores allocated to the latency critical application, and the y-axis shows the number of cacheways allocated to the latency critical application. The blue curve represents ISO load lines at a load of 20% of the peak load of the application on the server. The curve shows that the application is indifferent to an allocation of 3 cores and a single cacheway or a single core and 10 cacheways. These allocations are equivalent as the application can meet a load level of 20%. Similarly, we have different indifference curves for other equivalent allocations to meet other ISO load conditions of 40% to 80% as illustrated. However, the indifferent curves are power analysis. Of all the equivalent allocations identified by the indifference curves, the least power consuming allocations are shown using the dotted red lines. These intersect the indifference curves at allocations identified as A, B, C, and D. By operating the primary latency critical applications in these allocations, we can reclaim more power headroom for the best effort application. We can also reason about the resource needs of the best effort application using the Edgeworth-box. Here, the bottom left corner represents the allocation for the latency critical application, and the top right corner represents the corresponding spare resources made available to the best effort application. For example, when the latency critical application receives an allocation of 10 cores, the best effort application would receive 2 cores. The region highlighted using the yellow strips represent the spare resources that a best effort application is likely to receive if we were to operate the latency critical application as identified by the power efficient allocations. For a placement to be efficient, we need to collocate a best effort application whose power efficient allocation falls in the highlighted region. In this illustration, the spare cache capacity decreases more rapidly than compute cores. Therefore, a best effort application that derives higher performance per watt from cores as opposed to cacheways will be a suitable candidate for effective collocation. We can systematically capture these insights for key types of direct resources and an indirect resource of power using an indirect utility function. Here, we use a well-known utility function called Cobb-Douglas utility function. Prior works have shown that Cobb-Douglas utility function is well suited to capture performance of the direct resources like cache capacity and memory bandwidth, as it is able to capture the resource substitution behavior illustrated in the indifference curves. In this work, we observed that Cobb-Douglas indirect utility function is able to capture the utility of direct resources in the presence of a limit on the indirect resource of power. This utility function takes the form of an optimization problem, but the goal is to maximize performance we derive from the direct resources such that their total power draw is less than the power limit. This function has the components to capture the direct resource of type J allocated to an application, denoted as Rj, the marginal performance that we derive from the direct resource, denoted as alpha j, and the marginal power needs to use the direct resource, denoted as Pj. There are analytical solutions to the Cobb-Douglas indirect utility function to derive the optimal allocation of direct resource that maximizes the performance under a power constraint. Specifically, we want to allocate resource in direct proportion to its marginal performance benefit, denoted as alpha j, and inversely to its marginal power needs, denoted as pj. Higher value of alpha j over pj represents better power efficiency of the resource as we derive higher performance per watt and consequently a more need for this resource. We use the Cobb-Douglas utility function to reason about resource preferences and illustrate that we can arrive at an entirely different placement decision depending on whether we account for power as a constraining resource. Alpha j in the Cobb-Douglas utility function captures the preference for a direct resource as it captures the marginal performance. The x-axis in the plot shows a latency-critical application spins as well as its best effort candidate workloads, LSTM training, PB-zip compression, RNN training, and a graph processing workload. The y-axis for each application shows its relative preference for cores and cacheways. Note that the preference does not account for the power needs. As we can see, if we do not account for power needs, Sprints prefers more cores than cacheways. Therefore, if we do not account for the power needs of the best effort applications, we would make the decision of placing LSTM against pings as it derives higher performance from cacheways than cores, a completely different set of preference compared to spin. However, when we account for marginal power needs as captured by alpha j over pj, the resource preferences change drastically. When we explicitly account for power needs, Spinks prefers more cacheways than compute cores as it derives higher performance per watt from cacheways. In this case, it's better to place graph alongside Spinks as it can derive higher performance per watt from compute cores than cacheways. So, power constraint impact resource preference and consequently the collocation. In this work, we designed a framework, Pocolo, to capture these insights. There are three main aspects to Pocolo. Modeling and characterizing the application using Cobb-Douglas indirect utility function, cluster level placement management using utility function parameters, as well as server level resource management also using the utility parameters. Pocolo uses measured power and performance characteristics of the application to capture the marginal power needs of a resource and marginal performance gains in using the resource. Although Cobb-Douglas utility function is a nonlinear form, we can use log transformation and use linear regression to derive the model parameters. We can use the marginal power needs and performance gains to identify resource demand for the latency critical application and consequently the spare resource which can be made available to the best effort application. We can use these to estimate the performance benefits of placing a best effort application alongside a latency critical. The cluster manager uses the performance estimates to identify an assignment that maximizes the overall performance of the cluster. Given the performance estimates, there are standard methods to solve this. We use a linear programming solver to identify an assignment that maximizes the overall cluster. The server manager measures the load and the latency slack in the tail latency for the latency critical application. Upon a significant increase or decrease in the latency slack, it changes the allocation configuration to the power efficient configuration for the current. We evaluate Pocolo on a small-scale experimental platform comprising of Xeon 2650 servers, which have 12 cores, 20 caches, 256 GB DRAM. These servers have an active power of 130 watts and an idle power of 50 watts. These servers allow for power monitoring using Intel REPL power meter. These servers allow for cores and cache partitioning, and they also allow for core frequency scaling. We evaluate co-location of representative latency critical application and best effort application. The latency critical application spans domains of speech inference, image inference, web search, and storage service. The best effort applications are representative of deep learning training, compression, and graph analytics workloads. We present the highlights of the results here. For more details, please take a look at the paper. We compared Pocolo to power and hour strategies at cluster level, which is about placement, and at server level, which is about management. Compared to power and hour strategies, Pocolo achieves 18% higher throughput and 8% reduction in energy use. This translates to 16% improvement in the total cost of operation. This is because of efficient use of server capacity, power capacity, and energy. In summary, data center operators need to jointly manage server resources and power in order to achieve maximum returns on their data center infrastructure. In this work, we address this problem for a specific scenario of placing and managing opportunistic workloads in a private cloud. We show that we can systematically reason about resource preferences for applications in the presence of power constraints using principles of economics. And we show how we can use these methods and metrics to make cluster level placement decisions as well as server level management decisions. We prototype Pocolo and show the performance and cost benefits of our approach. Thank you for listening to my talk.